Okay, so what I want to do is talk a little bit about elementary matrices. Remember in section 2.2, you had an algorithm for finding the inverse of a function, the inverse of a function. And that algorithm works for any square invertible matrix. Well, for any square, yeah, for any invertible matrix. And there's a proof of why that algorithm works. And I think it's important that you understand a little bit uh, about the proof. The proof is in your book there, uh, right after theorem 7. And in order for that proof to make sense, I have to talk about elementary matrices a little bit. So what I'm going to do here is I'm going to write down 4 matrices. Okay, 4 matrices. All right, 1, 0, 0, 0, 1, 0, 0, negative 2, 0. These are 3 by 3 matrices. Okay, and then 1, 0, 0, 0, 1, 0, negative 3, 0, 1. And then finally 1, 0, 0, negative 2, 1, 0, 0, 0, 1. Okay. And then I'm going to have my matrix A. So what you're seeing here is I'm writing out a matrix product. I'm writing out a matrix product. Right. One moment here. So 1, 4, 7, 2, 5, 8, and 3, 6, 10. Okay, this is going to be called matrix A. This matrix here, I'm going to call E1. That stands for an elementary matrix. The next matrix is E2. That's another elementary matrix. And the third matrix there, well, it's if you go to the left there, that's another elementary matrix. So, right. So I'll explain. I'll explain. Maybe. Oh, yeah. Hold on. There is one error here. Thank you. Thank you. Good catch. That should be a 1 there. Yes. Yes. Thank you, Mikhail. Thank you. Okay. So you see, what an elementary matrix is if if you look at like this matrix E1 here, okay? If you were, I'll kind of put this off to the side. If you were to take this identity matrix, whoops, and you were to do one row operation on it, you would get an elementary matrix. So for instance, if you were to take negative 2 times row 1, add it to row 2, and put the result in row 2. Okay, just try to make this look good. Okay, what you'd have is 1, 0, 0, negative 2, 0, 0, and 0, 0, 1, right? So by doing one row operation, again, taking negative 2 times the first row, adding those numbers to the second row of numbers, and then replacing the second row, hold on here, I'm having a, yeah, you're right, hang on here. I'm being distracted a little by this. Okay, now hold on, what did I do wrong here? Oh yeah, thank you. Absolutely. Okay, so by taking the first row here of the identity matrix, this is the identity matrix, I sub 3, by taking the first row, multiplying it by -2, and adding that result to the second row, and then taking that sum and replacing the second row with that sum, we end up with this E2 matrix. Okay, and E1, sorry, E1. Okay. And that's what we have here. And every elementary matrix results from taking an identity matrix and doing one row operation on it. So like for instance, if you were to look at the E2 elementary matrix, what did we do to the identity to get the elementary matrix E2? What did we do to the first row? What did we multiply it by? Well, you have the identity matrix, you multiply the first row by a number. Good, that's right, Mikhail. -3 times the first row. No, -3 times the first row plus row 3. Put that result in row 3. Okay. And the third elementary matrix is you take the second row, multiply it by -2, and add to the third row. Now, what we do is when we do, like for instance, when we are trying to, like let's say I want to get the matrix A in upper echelon form. Okay, I want to get the matrix A into upper echelon form. Okay, or let me just hold on. Let me say the right word here. One moment. There's so much terminology. Hold on. Just one moment. Well, okay. Here, I want so you see how these matrices here, the matrices E3. So if you look at them, they have a triangle of ones. No, they have a triangle. I'm not saying this the way I want to say it. You have to forgive me. I'm not saying this the way I want to say it. So remember when you get a matrix in echelon form, below the diagonal, well, hold on. Something I want to say here. So if you notice, there's a diagonal of ones on all of these elementary matrices. And above the diagonal of ones, okay, what do you see? For E1, E2, E3, if you look the diagonal of ones, what are the only numbers you see? Above the diagonals, above that diagonal of ones. That's right, Bella, just zeros. Just zeros. And below the diagonals of ones, you see triangles of numbers. So these triangles where one of the numbers is non-zero. So these elementary matrices, these are called lower unit triangular matrices. Now, if we had a situation where we had ones along the diagonal, we call it, so lower unit triangular matrices, unit means because we have ones along the diagonal. If we had zeros below the diagonal on all the matrices, and above the diagonal we had like non-zero numbers, we would call that upper unit triangular matrices. Now, what's the effect of taking lower unit triangular matrices and multiplying it by the matrix A? Well, let's take a look here. Let's take a look. So first off, I'm gonna multiply E1 by A. Okay, we're gonna multiply E1 by the matrix A. When you do that, what's the first row of E1 times the matrix A? What's the first row going to be? So we're doing matrix multiplication. So you're taking the first row. Okay, well, and multiplying it by each of the columns. So what's the first row? What are the numbers going to be in the first row? Come on, this is easy. This is easy. What I mean is I want to know, so there are 9 numbers here, right, in this matrix, 9 numbers. You're taking a 3 by 3 matrix, a 3 by 3, and multiplying it by another 3 by 3. So the resulting matrix has to be a 3 by 3. There are 9 entries. I want to know what entries are in the top row. So that's taking, 100 times. Okay, that's what I'm looking for, Belen. That's right. So 147. Okay, now if you now multiply the second in E1, if you multiply the second row by each of the columns of the matrix A, okay, you're going to get 0, -3, -6. Okay, that's what you are going to get. And if you multiply the last row by each of the columns, well, you have a 0, 0, 1 in the last row, so that's not going to change. I mean, the effect is just going to be 3, 6, 10. Okay. So look at what the elementary matrix 1 was. Elementary matrix 1, what it did, how did we get the elementary matrix 1 from the identity matrix? We took -2 times the first row and added it to the second row, and then replaced the second row with that result. Well, this product matrix here, this E1 times A, it would be taking the first row of the matrix A, the 1, 4, 7, multiplying it by -2 and adding it to the second row of the matrix A and replacing the second row with that result. So we can model a row operation such as this. We can mathematically model row operations we do on matrices by pre-multiplying the matrix A by elementary matrices. That's a trait of elementary matrices. That's exactly right. Okay, and now what we're going to do, let's take now the E2 times this E1 times A. Okay, well, E2 is 1, 0, 0, 0, 1, 0, -3, 0, 1. Does anything happen? Did the identity matrix, to get that second elementary matrix, did the identity matrix change at all in the first two rows for E2? Was there any? I mean, the identity matrix for E2, the first and second rows just look like the identity matrix, right? So that means when we multiply the E2 times that second matrix, the first and second rows aren't changed. But the third row of this second elementary matrix resulted by taking -3 times the identity matrix, times the first row of the identity matrix, and adding it to the third row, and then replacing the third row with that result. So we'll do the same here. And you'll see we'll get 0, -6, -11. Okay. Now what you're going to do is you're going to bring down E1. You're going to bring down E1. 1, 0, 0 times 0, 1, 0 times 0, -2, 1. And you're going to multiply that elementary matrix by this matrix, which is I'm sorry, that's E3, right? E3. You're going to multiply that by the E2 times E1 times A matrix in that order, right? When you do that, well, the E3 matrix, that elementary matrix there, results by taking the second row of an identity matrix, multiplying it by -2, adding that result to the third row, and replacing the third row by that result. So when we multiply E3 times this matrix here, what we're going to get is, well, 1, 4, and 7 aren't affected. 0, -3, and -6 are not affected. But we're going to get this in the denominator. 0, 0, and hold on here, and 1, I believe, right? Check my math on that. Okay, Belen, thank you. Thank you. Okay. So what do we have here? What do we have? Thank you, Belen. Thank you, Mikhail. What do we have with this matrix? What form is this matrix in? What form is that matrix in? Echelon form. Okay. And we denote that with the letter U. Okay, we denote that typically with the letter U. So that's an echelon form. That's an echelon form. Now, one moment here. Upper echelon form. Because below the diagonal you have zeros. All the non-zero numbers are above the diagonal. Okay. Right. So let me just see here. Okay. So we could have done those. I mean, the row operations, like getting this matrix A to this echelon form matrix U up to, I mean, okay, you have of course done row operations in your mind, and then written down the equivalent matrices. Okay, but what I'm trying to show you here is we can model row operations on a matrix by taking the matrix A and pre-multiplying that matrix A by elementary matrices. Okay. Now, if we wanted to get this matrix, it's in upper echelon form now. If we wanted to get that matrix, it's in echelon form. Let's just call it echelon form. Let's keep it simple, right? Echelon form. Now, if we wanted to get that matrix in reduced echelon form, we'd have to multiply by some more elementary matrices. And notice that the lower unit triangular matrices got this matrix A into echelon form. If we want to produce zeros above the diagonal, if we want to produce zeros in this upper triangle here, perhaps 3 elementary matrices are needed, and those would be upper unit triangular matrices. Okay, so I'm just trying to sort of give you a little feel for this. So now, how is this helpful for understanding the concept of finding an inverse of a matrix? Well, let me show you. Let me show you. So let me go ahead here. Let me see. Just got to find it. One moment here. Hold on. I just got to find it here. I have it. I have the book. I just want to, get it to show. There we go. There we go. So here, they're saying that in theorem 7, any square matrix is invertible if and only if A is row equivalent to the identity. In other words, the sequence of row operations that reduce the matrix A to the identity also transform the identity into A inverse. And the way you can show that is if you look here in the proof. Okay, so what they do is they say, okay, actually here, let's focus here. All right, hold on. Of course, I screwed it up again. Hold on. Gotta go back. All right. Give me some love here. Give me some love. There we go. Okay, so what does that mean, what I've highlighted there? It means doing enough row operations on a matrix, say, that's invertible, would reduce it to the identity matrix. That's equivalent to multiplying the matrix, say, by a sequence of elementary matrices. Now, what we can do to that equation, to that matrix equation, is both sides of that matrix equation, we can multiply it by the inverse of the product of those elementary matrices. Well, on the left-hand side, the inverse of that product times the product will equal the identity. So what happens is now is that the matrix A just equals this inverse of this product of elementary matrices. Okay. So that's fine. That's fine. But what now? What now? So let's take a look at the inverse. The inverse then would be the, let me just maybe take a few highlights off here. Okay, the inverse of the matrix A would be the inverse of the inverse of those sorry, the inverse of the matrix A would be the inverse of the product of those elementary matrices, okay, that reduce the matrix A to the identity. But the inverse of an inverse is simply okay. So therefore, what this means is that if we take the identity matrix and multiply it by the sequence of those elementary matrices, and that means do the same row of operations to the identity matrix, which you did to reduce the matrix A to we used elementary row operations. Let me just unhighlight a few things here. Hold on. I got a little bit too much highlighted here. Let's focus here. So we use row operations on the matrix A to get it into reduced echelon form, which would in this case be the identity matrix, because the matrix A is a square matrix. It turns out at the bottom there in the highlighted part that the inverse of the matrix A can be found by doing one moment here. The inverse of a matrix A can be found by doing those same row operations to the identity matrix. And that's what we actually, that proves the algorithm. That proves the algorithm for that we learned for finding an inverse. It proves the theorem. The theorem above, and it justifies the algorithm for finding the inverse. Okay, so are there any questions on that? Yasin, did you have a question? Yasin? Okay, well, are we feeling how many feel that this was kind of nice to see why this algorithm worked, why it works, to see that little proof that they give there after theorem 7 and understanding these elementary matrices? Was this okay, Mikhail's liking that, Marcella, Cameron, wonderful. You see in Jonathan too. Excellent. Excellent, Balin. Wonderful. Yeah, I want you to appreciate this. You see, in a lower level course, and I've taught lower level courses, you would learn the algorithm, but you wanted to for finding the inverse. Uh, you know, even when I taught high school back in the day, we used this algorithm for finding inverses, but you didn't really learn why it was true. And you now, because you are in Math 284, you have the mathematical maturity essentially to appreciate a proof like that. Okay, I'm going to stop the recording here. Excellent. Excellent.